what I'm pretty sure Tom will talk about, if he's true to form, will be the need to be able to replicate data, to share data across multiple nodes, do RDMA access of this persistent memory. That's what I'm expecting he's going to talk about. And then after, our final speaker will be Kevin Deerling from Mellanox, who is a leading fabric supplier who was probably going to go through their commitment and what their view is on this as well. So this is, I think, if you look at what we've done today, what we've covered is what's been done today. I think this is where the future of the NVM programming twig is, and what the next steps are. So and I hope you enjoyed these last two sessions. This is the future. This is what's next. Thank you, Tom.
What's the time protocol here?
You got 30 minutes.
Oh, a full 30.
Full 30. Yeah, we got ourselves back on track.
Okay, thank you.
Yeah, I was good to you.
All right. Good. Well, there's 20 slides, so I'll do it in a minute and a half. And well, I'll leave something for questions. I'll try to leave something for questions. So hi, I'm Tom Talpey. I'm an architect in the server division, responsible for the network file system SMB3 and SMB Direct. This presentation is similar, but contains more detail toward the end to a presentation I gave at the SDC, the Storage Developers Conference back in September, and reflects going remote at low latency. I've changed the title somewhat. The key is remote access to ultra low latency storage. How do we preserve the latency of the storage when we access it remotely, right? Why do we want to access it remotely? How will that remote access, what's the workload for that remote access? And then how can we provide that same latency story for remote as well as we have it for local? So the problem statement is a little brief. Provide applications with the remote access to non-volatile and or persistent memory. I kind of differentiate those two just a little bit. And as used as storage with ultra low latency. So remote access, ultra low latency. Those are the key words here. And then second, examine the storage protocol and the RDMA protocol extensions that may be required. I argue they will be required to actually provide this. And we have to look at the workload to figure out exactly where to throw our weight, right? And so I'll just talk a little bit about those two things. Okay. It's interesting. Today, there have been some interesting discussions that focus on some things that are near and dear to my heart, my passion, but are not part of this presentation. And I guess I just want to mention them. One of the most important one is capturing applications, right? Providing lower level semantics that benefit these applications is one thing, but how do those applications use those semantics is just as important. What's the API? What's the semantic? What are the error semantics? That's one of the real knots that you run into when you try to untie this rope. And to me, the traditional APIs that they're already used to are very, very, very compelling for them, right? And those APIs flow through layers as they are remoted. And for storage, it could be blocks, but honestly, I believe it's files. And you'll see two file protocols near and dear to my heart here. So by focusing on these upper layer storage protocols and how we enable their lower layer PM access, I think we can provide a bridge to application adoption that's much shorter and much easier for those applications to cross. So just bear that in mind. I'm going to talk about the ecosystem, and I'm going to mention it in a storage environment, okay? I'm going to focus on enterprise and private cloud capable storage protocols, the traditional protocols that we are using or planning to use imminently today. This could include actual RESTful HTML, I don't know, but let's focus on the existing file protocols that are today RDMA enabled. And their characteristics are really important. They're scalable, manageable, and broadly deployed, right? They're out there, they work at scale. They're manageable, so they can actually be deployed. They provide authentication and security, and by security I mean both integrity and privacy, all right? Security is a great big hairy word, but In the storage environment, we're going to talk about those two attributes of it. And finally, they'll natively support parallel and highly available operations. So multi-channel, multiple paths, redundancy, trunking, that kind of thing are very important to these protocols. And they provide them today, or at least many of them do. And my three examples that I mentioned here are SMB3 with SMB Direct, NFS, RDMA, and ICER. ICER is the iSCSI extensions for RDMA. It's a block protocol, very different from the other two, but relevant. And there are others, but I'm not going to talk about them. Workload. Application workload, it's all about writes, and I'm going to try to justify that statement. I left out a couple slides from SDC, so I kind of leap into this because I want to talk more about the back end of it. But this is important to start it up. Writes with possible erasure coding or at least striping, mirroring, at least some sort of redundancy is really important to all these applications, right? It doesn't count until you've put multiple copies of the data into multiple failure domains. You got to get it off the box before safely off the box before you can complete the I/O. And so those writes greatly multiply the network I/O demand. And this is just a little picture that I stole from Windows Azure or Microsoft Azure that shows some of it. The write workload is primarily small and random today. And it comes from virtualization workloads primarily, right? They're doing ordinary file system or storage I/O, right? And every time they perform a write, the write gets magnified. And that's what this little animation does. So in comes a write from somewhere in the cloud or wherever. That write has to go to several other nodes, right? And then afterwards, an erasure code is calculated, which also has to go to all these nodes. And so there's this tremendous amplification of the write as it occurs, right? To provide that redundancy, availability, recoverability, all the other attributes that we need to call it actual storage. So it must be made replicated and made durable. And that single write hops. We call this the two-hop issue, where you send it to a server and the server performs more I/O on the back side. All such copies must be made durable before responding. So that little upward right arrow on the top didn't occur until all the commits had occurred, all the green commits had occurred. And then there's one other thing to mention, and that is that reads are actually not very important. Remote reads are not very important. And the reason is that we've probably cached a copy, or we've got some sort of copy that's close to the source that we can satisfy the read from. But every once in a while, we have to recover something. We have to go recover a node that failed, or remirror and restripe and recalculate erasure codes. So the small and random ones are, in fact, latency sensitive. We usually take care of those with locality. Larger ones are somewhat more forgiving, but recovery and rebuild are significant. So we're going to focus on writes, because satisfying that one write can't be done until other writes take place. And there's one other source of latency concern, and that is the API. APIs also shift the latency requirement. Traditional block and file I/O are often parallel. And parallel, sequential deep queue I/O style hides a lot of latency, right? Because you get a huge throughput, and each operation is basically sharing the latency of all its neighbors. That parallelism is gone with memory mapped and PM-aware APIs, right? They have a load store paradigm, right? They're synchronous, right? In fact, if they don't complete quickly, the machine will probably throw a bus error of some kind. So the memory latency is critical. Memory speed latency is critical. And second, the parallelism goes out the window because these are synchronous instructions. Local caches can improve the read, but it still can't improve the write because we can't lie about the commit. And many layers are involved. As we perform a traditional storage I/O, it goes down through SMB, PNFS, iSCSI, whatever. It proceeds to the network layer, RDMA. And it actually, there are I/O buses involved here, right? The commit and the PM, and it sits on an I/O bus or a memory bus or I don't know what. But these are all protocols, and they all beget one another. So Let's not forget them. Okay, just a little bit of background because this is a PM conference. I'll just mention an RDMA model. All the protocols I mentioned before perform RDMA in roughly the same way. All right, they use the RDMA layer in roughly the same way. There's a lot of little details, but there are two important things. A write begets something called an RDMA read. When you write data from a client, from a data source, the data sink, the server will pull the data. So you advertise the data, the server pulls the data, and then the server completes the I/O. So it's a 4-trip, 2 round trips on the network to satisfy a write. And additionally, that write begets a few interrupts. Those little lightning bolts are interrupts or completions that occur on either side. Those interrupts add overhead and they add latency, right, for the context switch. So they are undesirable. Reads are a little better in that the RDMA write is basically kind of free. It just sits in between the request and the response. And it doesn't generate an interrupt. It just moves the data. A consistency guarantee says where it goes, but it doesn't always, there's some durability issues that are hiding in here that RDMA has historically not addressed. So I don't want to drill down too deeply on RDMA, but I just want to point out that there are sources of overhead in the RDMA transfer that are undesirable for persistent memory. And I'll just try to show you why. This is, I guess I already talked about this. Interrupts and work requests. Actually, there's one more source, and that is the actual server request processing. Right? You send the server a message that interrupts it. Well, it needs to do some work, right? And so that server request processing is additional latency and additional overhead that may not scale. So they need to be included in the calculation. It's something that we'd like to get rid of. So last September, I proposed the adaptation of the upper layer storage protocols to use something I call RDMA push mode. Right? This would be to satisfy a write. The data source would be allowed to actually push the data instead of sending a request to pull the data, which is what they do today. This requires a change to both the upper layer and potentially, because of persistent memory, the RDMA layer. The upper layer is fairly simple. There actually are some upper layer storage protocols that enable push today. However, the 3 big ones that I mentioned don't. So basically, it involves a sort of a pre-registration, which you can see up there at the top in those 3 black, the 2 black interchanges, and the 1 black registration. The client would request the server register a region for its use. The server would perform a registration and return a handle to that registration. At that point, the client can basically party on using traditional RDMA to read and write that memory. But it's done from the client with absolutely no server interaction. It's done entirely by the server's NIC. And so there are no interrupts here, right? You can see a big blank line in the interrupts. There actually are some interrupts on the left for the client, but that's okay. The client's expecting that. It wants to know when the work is done, etc. I didn't even bother to put them there. There is one new line on this thing called the RDMA commit, and it's kind of sitting in there with the diamonds on the end of it. And that's what I'm going to talk about in a second. But those writes for persistent memory are not durable. They enter something called the consistency space of the data sink, but they don't enter the durability space of the data sink. And so that's an extension that we need to provide for persistent memory push mode, right? And we're going to talk about that in a minute. There are some little problems, though, because if the client is modifying the data, this is the same problem we saw in the presentations about the file system. If the application is modifying the contents of the file system without ever really hooking any server code, any file server code, how does the file server know that the data has changed? How does the file server know to update metadata or to manage data and things like that? So the client may want to periodically update the server via some sort of protocol in a very similar way to the way local file systems will allow applications to notify the file system of these changes. Of course, this is a matter for the upper layer. I'm not going to talk about it in any great detail, but I'm going to show 3 examples of how it might happen. Second issue is that the server may need to call back to the client. So this is a little different from the local case. Now the client and the server are running in 2 very different failure domains and management domains, right? They're running on 2 different machines. So occasionally the server may need to pull back its resources, may need to close a window, revoke access, do whatever. And so callbacks are very important. And finally, the client needs to tell the server when it's done as more messages. So hypothetically, I just had 3 examples. I don't think I'll spend a lot of time on this, but in SMB3, there'd be a setup, a write, a read, a commit, a callback, and a finish. NFS RDMA is pretty much the same thing. And ICER, interestingly, is pretty much the same thing. Although ICER has a few differences in that it doesn't have existing primitives for some of these operations, or at least I don't think it does. And we need to take this to the iSCSI ICER community. But it still provides for that same model where the data source, the initiator or the client, can modify data on the target or server transparently to the server processor. And so it will occasionally require the initiator to tell the server that something happened, and it may occasionally allow the server target to call back to the initiator to either prevent it or modify it from doing other operations. And so these are basically 3 upper layer protocol dialogues that need to happen in the appropriate communities. Okay, down a layer. The RDMA protocols need a remote guarantee of durability. Traditionally, RDMA provides only a guarantee of visibility or consistency. That is, that the data is moved from one system to the other and can be viewed or seen in a consistent way at certain points. These points are generally completions. Completions are basically signaling from the NIC to the processor. That signaling has a couple of important functions. The first is that it passes control to the processor code, which can do whatever it needs to do to flush caches or to make a hardware, software synchronization of some kind. And second, that they can actually manage their work requests and they can manage the flow of control between the upper layer and the hardware. And so these completions do not mean that the data was actually placed in memory, actually committed to durability. It just means that they've arrived at the space. Generally speaking, that they're sitting in a cache somewhere on the motherboard, if you will, on the bus of the system. And so we need a stronger guarantee. We need some sort of commit operation to actually get it, over the goal line and into durable space. There's another interesting issue, and that is that ordering is also only guaranteed at certain points in the process. RDMA writes are actually unacknowledged and can be processed in almost any order. But if an operation goes after an RDMA write, then completion of that operation does have implications on prior RDMA writes. And so there's some very interesting subtleties that come into play with respect to the error semantics. If something is lost or failed, where did that failure occur and what bad things might have happened in between the last successful point and that error? So there are some really interesting problems when you go remote that guarantees you don't always have when you're operating locally. Many of them are very similar to local error conditions. They're just lit up more brightly when they're remote. So, we've been doing a lot of work in the NVM TWG about identifying what these are. But I think the protocol can help us here. And the last thing I want to mention, this is kind of a long one. I'm only halfway through. How am I doing on time? There are certain platform-specific guarantees that can be made, but it's really important that the remote client can't possibly know them unless we define some sort of really complicated upper layer exchange. A lot of people say, well, you just RDMA read the last byte, and that'll guarantee that all the bytes appeared. No. In fact, it doesn't mean they appeared. It means that they entered consistency space, but they did not necessarily go into the destination memory. And you can turn off all the caches on the server and maybe make that guarantee, but A, the client can't know that. He's going to be doing that RDMA read from now to eternity, and it may or may not help. And B, you've probably just turned off a lot of really interesting, important performance features on your server, right? So they're very, very, very undesirable. All right, how do we do this? There are two obvious possibilities, and the first one that comes to everybody's mind is, let's do an RDMA write with a placement acknowledgement, okay? Let's set a bit in the RDMA write that says, you must place this data all the way to memory. Well, guess what? It won't work. It's a simple API. It seems very simple, but the disadvantage is it significantly changes the write semantic. The RDMA write is actually not acknowledged. It's a streaming operation with no acknowledgement. It just simply happens. It's just like a PCI write. It's fire and shoot and scoot, fire and forget. It's just off into the space somewhere. You don't actually know when it's done. It happens on the wire. It happens on the PCI bus. So it requires creating a write ACK. That write ACK would actually have to happen on the PCI bus so that the NIC could do it, as well as would have to have an RDMA write ACK. And then finally, you'd have to block the write, right? Which doesn't happen today. The write today unblocks as soon as the data is buffered. So it would significantly change the RDMA protocol to do that. You could do it, but you'd slow it way down. It wouldn't be an RDMA write anymore. It wouldn't be fast anymore. It'd be a round trip on the network, and it would be a blocking round trip. So it'd be really bad. The second, which I'm proposing, is an RDMA commit. It's a new operation. It's flow controlled and acknowledged, kind of like an RDMA read or an atomic. It's actually a two-way operation. Send a message to the server does some stuff. Well, the server's NIC does some stuff, and then responds. It's a new operation, so it requires a protocol change. But it's similar to the flush that we're talking about in the SNIA. It's similar to the flush we operate on with the CPU instructions today. It's just very similar to the operations we do today. So it's a little harder, but it gets us where we want to go in a much more direct way. It doesn't have any dead ends. The concept is it's a new wire operation. It's implementable in all protocols, by the way. There's nothing special about the protocol here. It's a conceptual operation. It's like a verb. The initiating RNIC provides a region list and other parameters. The receiving RNIC performs it, pushes the pending writes, performs the commit, and then responds when durability is assured. So it's a blocking operation, but it's a parallel operation in my view. So it operates like an RDMA read. There's a limited number of, there's a queue depth to it in effect. It's semi-desirable to include other semantics, and this is where we'll have a dialogue in various protocol specification areas. Atomically placed data after commit. Right? You want to commit a big slug of data. When you're done, you may want to commit a little pointer, like a log write, okay? I've dropped the big log record. Now I want to update my pointer to point to the newly dropped log record. The second thing is immediate data or an entire message. You want to signal the server, the CPU on that side from time to time. Not always, but a lot of protocols definitely. And the size of that data and the semantics of that data are important, but also the ordering of that data is important. You want to signal it with certain guarantees of what just happened. So we have to think those through. The actual decisions for what we do, I think, will be workload dependent. I think there may be more than one behavior here. There's going to be some optional behavior filtered in here. There's a second piece to this for the local API. And the local API is really interesting because if you do the local API cleverly, you can almost avoid doing anything with the protocol. And so I just want to sort of spin this around and say that there are other ways to approach some of these workload-dependent behaviors. We're going to need a new persistent memory registration verb that's going to have a PM type to indicate what it is, right? Is it regular memory? Is it persistent memory? Is it PCIe attached memory? I don't know. But the NIC is going to need to know exactly what type of memory is at this region. And the second, there's a mode. And the mode could be read or write, but it could also mean cacheability. It could mean that the CPU may want to read this. So there are some flags that will flow along with this. Transparency is possible if we get some of these right. If you're taking a completion and signaling the CPU, many of these things can flow transparently. You could do an RDMA write with immediate to a region that was tagged in a certain way and not have to change the protocol, I believe. You could do a send and a receive it into PM and not have to change the protocol, I believe. So those are some things to think about. I'm going to fall way behind here. I'm sorry. We do need some PCI extensions to do this if the NIC is PCI attached. But the NIC may not always be PCI attached. It may be on a memory bus or within the CPU complex. And new protocols are available to it when it sits on alternative buses. So don't limit your thinking to the PCI bus, I think. It would be weird to see a network device on the memory bus. Expectations, single-digit microsecond. Remote write and commit. We have some data from SDC that Chet Douglas of Intel simulated that show this on iWarp InfiniBand today. So we expect that we can get to some very compelling microsecond latencies. We believe that read can flow roughly the same as write, but obviously we don't need commit. We believe we can do this with no server interrupt and a single client interrupt. And with parallelism and multi-channel type things, we can reduce those interrupts with moderation and batching. And where the discussion goes is interesting because I think it leaves the PM community and enters all the other communities that I mentioned before. The upper layer file system, the middle layer RDMA, maybe even the fabric, the motherboard, all kinds of interesting protocols and interactions between systems when memory and network are welded together so closely start to happen. And so I believe that this dialogue will grow in the next couple of years. And I believe a lot of communities will be analyzing this. That is the end. We have time for a couple questions, I hear. Yeah.
Does this contemplate say a home chassis and an extended or expansion chassis connected over, say, PCIe like Oculink? And would all these transfers occur in that realm, or do you expect it to go over some other transport medium?
Yeah. What's the form factor of the complex here? Is it a PCI Express with multiple chassis, or is it a network in between them? Is that a fair summary of your question?
CPU complex talking to storage over PCIe.
Yeah, well, of course, that happens today, right? The CPU complex may have a storage card plugged into PCIe. I believe you could actually have a no local storage device that would have compelling performance with just an RDMA card in it, if you chose your RDMA fabric well. At SDC, Roland Dreyer of Pure had a presentation about using PCI Express peer-to-peer for for forwarding operations, using it in effect as an RDMA fabric. And so, I mean, there are designs that do that today. Yes, in a word, you could see these. All right, thank you.